Okay, so in this video we're going to be talking about symbols, and like we might have seen before, um, there are many different data types that Racket allows you to work with. This is just another one. So symbols are actually relatively easy. They're kind of like strings in that they are a representation of characters that you can use, but the difference is that symbols actually can't have any spaces in them. So if I were to type in my symbol A. It's not like there's going to be a closing quotation, like that doesn't exist. So it's just going to be an error actually. So this variable is not defined. It's thinking that there is a variable there. If I do my symbol, then it presents out my symbol with the quotation. And that's actually how you represent symbols. You put a quote, a single quote, and then whatever the name of your symbol should be. And symbols represent themselves literally just by name. You can define things to be symbols. Define, my const and to be a symbol 3. But the thing is that the symbol 3 is kind of self-explanatory, so it doesn't make much sense to dedicate a constant to representing that symbol. So symbols are useful simply because, one, they allow us to compare, they allow us just to make comparisons pretty easily. By comparisons, I mean comparisons for equality. You can't do symbol less than or symbol equal to. And they're just useful for representing different types of data that you might want. For instance, if you're checking, blood types, you'd want to make sure that you're giving someone the proper blood type. You could check, symbol equal, the blood type of a person, let's say Kate type, and then let's say you only have O negative in the bank. And we can represent O negative as such, and we can define define Kate type to be O positive. So if we do this, we get a false, right? And if we can define Kate's type to be O negative, that'll be fine, okay? So symbols are definitely useful for situations when you just want, are these two the same or not, kind of result. Otherwise, you're going to probably be using strings, because they're more complex and they allow for better ideas. So symbols, you use them only when there's like very particular categories, a finite number of possibilities, and you're just comparing them for equality. They're a very simple data type. In fact, they're so simple that we're probably going to now just look at something else, since these are so simple. We're just going to take off this definition and remove this. We don't really need it. And we're going to talk about structs. Structs are actually really cool. They're a really cool part of Racket. Essentially what they allow you to do is to bundle together different kinds of data into one sort of object that you can treat. So here's the thing. Let's say we want to make, I have here a syntax for creating a struct named account. So this is a special case of the define syntax. So instead of just define, we're going to use define dash struct. This is a special define statement. It allows us to define a structure. And this takes two special arguments. It takes the name of the struct and then what its fields should be. Okay? Here you have to be careful that this is a left bracket, but we're not indicating that this is a function, right? You can't call a function name with one parameter money. This is specifying that account is the name of this kind of structure, and it has two fields, name and money. Okay? So whenever you define a structure, you get three kinds of functions that come along with it. You get the create function. This allows us to do things like make, and then the name of the actual structure. So that's specific to this kind of structure. We're making an account, and then you specify what should be inside. So we can say Jack Black is the name, and then let's say he has $500,000. So if we run this, we'll notice that everything happens smoothly. Oh, I spelled account wrong. If we run this, it's fine. Everything works because make account, this function was created when we defined this struct. So that's the create function. Then we have selector functions. In this situation, you notice that there's two fields. There's name and there's money. So we have a selector for each of those fields. So this means that we have account-select, account-name of a structure. Okay, so account name is going to work on a structure. So in order to minimize the amount of code we're writing, we might as well say define Jack. Might as well make it. I'm having this be the definition. So if I look at this, I realize that Jack is a structure because we're defining Jack to be a constant, which is of type structure. So if I call this, what it should do is it should expand Jack to be this structure and then realize that it's an account, and we can fetch the name of the account and produce it using this function. So it should produce Jack Black. If we run this, I can't spell account, I guess. It gives us Jack Black. In the same way, we can get the money he has. Money. And this time it should give us back $500,000. Okay? So those are the two selector functions. They work on the number of on exactly one parameter, and that is a structure of the proper type. And lastly, let's just look back at the create function again. When you're doing make account or any type of structure, you need to make sure that you give the right number of fields. For instance, if I only give, John Doe, then it's going to be mad at me because, I can't spell. I can't believe I've done this like that many times. Anyways, here it says it expects 2 arguments but only found 1. So because we defined the account structure to have 2 fields, you must have 2 arguments inside of the make account parameter. Interestingly, I can, put any data type here I want. Like, I could literally put the symbol 90 and everything runs fine. Simply because Racket doesn't check what type, is supposed to go where. In fact, for John Doe, I could literally put, something weird like true, and Racket doesn't care. All it cares about is that you give it the right number of parameters, because it doesn't know that name is supposed to be a string and money is supposed to be a dollar value, or not really a dollar value, but like an integer, or an integer with like decimal places, right? This works here. Everything's fine. So the last kind of function that we have is a predicate, and this, all it does is it checks whether this is an actual account structure. So if we do Jack, this should return true because Jack is a proper account structure. It has 2 fields. Everything should be fine. So it gives us a true value, and you can use this to make sure that your functions are safe. Because if we say, let's say we define add money, and then we're going to operate on an account, right? What we want to do is we want to create a structure that adds that kind of money to the account. So we'd have to do make account, and then the first field would have to be the account dash name of the act, because we want to preserve their name. And the second field, I'm just going to indent this like this. The second field should be, oh, I forgot a parameter here. It's like money. The second field should be the money that's already in the account, and then added to this money. So we would have to do account dash money of the account plus money. Okay. I'm sorry for this sort of like weird parameter, especially since money is the same in both the definition and the function. Maybe I should change like, money added. So basically this is going to create an account that has the same name, and the money should change by however much money we add. Okay? And in technicality, what I could do is for Jack, the name should be the same, but the money turns into, let's say, a symbol. So here, technically, everything is fine. But if I run add money to Jack, and I want to add $100, this is going to cause problems. That's very interesting. This is a symbol. And okay, let's just treat it as a string, 'cause this doesn't make sense. Anyways, so it expects a number as the first argument, and it's given a string. So here, what we can do is we can check whether this is an actual integer. Otherwise, things are going to go wrong. In the same way, you can give add money a value that actually isn't a struct, a proper struct. For instance, Racket comes in with the pause instructor. So if we do make pause in 3 and 4, this is going to fail because it expects an account and it's given a pause. So here's what we can do. We can check. In the future, we're going to look at a con statement, and basically the con statement lets us know is we can check whether it's an actual account, and if it is, then we can run this part of the function, because now that we know it's an actual account, it's not going to cause us any problems like not syntax problems but runtime problems, because the function figures out that this isn't an actual account, and then it encounters problems. So first we check if it's an actual account. Otherwise, we can say bad data given. So if we do this and run that, then it's going to tell us bad data given because it checks that ACK is an account. It realizes it's not, so it can't execute these and tells us, the bad data was given. Okay? This is like a safe way to construct your functions. Anyways, so we've discussed all three of the types of functions that you get when you create, when you have a structured definition. You get the create function that you do make account or make whatever type of struct you define as. If I define this as a bank, I can do make bank, and then I have to change all of these accounts to banks. And that's generally what happens when you create a struct. Also remember that Racket doesn't type enforce anything, so even though you may have intended the name and money to be a string and dollar value, nobody's going to really know. What you can do is add in your own definition, and what this might look like is a bank is, and then here you can say, well, name is str for a string, and then money is a number. And if you want to be more specific, if it's a specific kind of bank account or something, you can say this is an integer, simply because someone might have negative amount of money, or you can say it's a natural if they can only have positive amounts of money. So this is your own little way of enforcing type, in the sense that if someone is going to be dealing with your code, they will at least know what type you intended them to deal with. And you have to be kind of careful because otherwise your functions can fail. Obviously we don't need to do this, but we saw that instead of exiting gracefully and giving us an error message, it just broke. Okay, so usually it's a good idea to make sure your programs don't break and instead just give back a nice error message. But that would involve making sure that all of the types that you've got are actually the types you want to operate on. This is kind of it can take up, it's a lot of extra overhead checking for something that really shouldn't be checked, simply because whoever the client is might be inclined to read this to make sure that they're giving in the proper types. But that's really about it. I mean, after all, if you did give the proper like contract and everything for this function, everybody would know that ACC, the account, has to be a struct of type account. Okay, so that's pretty much it for structs. Let's go on to the next one.